We will talk now about the Laplace transform, and the Laplace transform is a transform actually, so is an operator that's really useful for mathematics and engineering. Now, what we see here is actually the definition of the Laplace transform, and the definition is actually an operator. So we have the operator L, and here we have a set. This set is the set of all the functions that are of the form f of t actually, and you could think of t as time in terms of time. Then for each one of these functions of the form f of t, we have a corresponding f capital of s, that's this integral here, and the integral, or this function, is actually the Laplace transform of f of t. So the Laplace transform of f of t is f capital of s, and this is the integral. I have s positive in order for the interval to converge, so this improper integral here has to converge in order for the Laplace transform to exist. Now, I understand that this is an easy definition. Why actually Laplace defined the Laplace transform this way is a very deep subject, and something that we could not analyze at the moment. So let's see basic things. The first thing we have to do here is to see that Laplace transform is linear. So if you have the Laplace transform of a times f of t plus b times g of time, that a and b are real coefficients, this is a times the Laplace transform of f of t plus b times the Laplace transform of g of t. This is the linearity condition of the Laplace transform. Now, let's start to calculate some very simple Laplace transforms. I want to calculate the Laplace transform of f of t when f of t is 1. So actually I want to find the Laplace transform of the function 1, of a constant function. How can I do that? Well, we remember we have the definition here, so in the place of f of t I have to substitute 1. So the Laplace transform of 1 is actually f capital of s, and this is integral from 0 to infinity of e to the minus st times 1 dt, where I suppose that s is a positive number. Of course, as you see, the only thing I have to do here is to calculate actually this integral. Let's calculate the integral from 0 to infinity of e to the minus st dt. Actually, this is the integral of minus 1 over s e to the minus st derivative dt, because the derivative of minus 1 over s times e to the minus st is actually e to the minus st. This is the formula that you should be familiar with from the basic integrals. So here, because I have the integral of the derivative, this is the derivative from 0 to infinity, and this is the value of the derivative, the value of this expression actually at infinity. So this value is the limit of minus 1 over s times e to the minus st when t tends to infinity, plus 1 over s e to the minus s times 0. So this is, remember that t is my variable, so s is a constant number, and this is minus 1 over s times the limit of e to the minus st. I'm writing that 1 over e to the power st when t tends to infinity, plus of course 1 over s times 1. Now take a look at that. Since t tends to infinity and s is positive, this expression here is plus infinity. E raised to plus infinity is infinity. 1 over infinity is 0. So 0 times minus 1 over s is 0, and I have 0 plus 1 over s, so it's 1 over s. What I found is that the Laplace transform of 1 is 1 over s. The second basic Laplace transform I will find is the Laplace transform of e to the power at, where a is a number such that s is greater than a, and s actually is the parameter that appears in the Laplace transform. So with this hypothesis here, what's the integral that we have to calculate? We must find f capital of s, that's integral from 0 to infinity, e to the minus st times f of t, and f of t is that. So e to the at dt. Here I have to find integral from 0 to infinity of e to a minus s times t dt. Now you understand why I have this restriction here, this constraint. I have this constraint because a minus c must be positive in order for the improper integral here to exist. Now, how can I find this? Easily. This is 1 over a minus s e to a minus s times t from 0 to infinity. So this is again the value of that expression at infinity. It means the limit of 1 over a minus s times when t tends to infinity minus 1 over a minus s times e to a minus s times 0. So here, okay, now I change the exponential function into 1 over e to s minus a times t when t tends to infinity. Now, why did I do that? Minus here 1 over a minus s, yes, times 1. So, what do you have here? Since s is greater than a, s minus a is positive. Since t tends to infinity, positive number times infinity is infinity, so 1 over infinity is 0. So we have 1 over a minus s times 0 minus 1 over a minus s. This is minus 1 over a minus s, that's 1 over s minus a. Of course, that's a positive quantity here because s is greater than a, and the final result is that the Laplace transform of e to the at is 1 over s minus a. Not difficult to find actually. We will continue in next videos. We will continue with finding some more basic Laplace transforms. Bye for now.